All right, so continuing on, this is allegedly lecture 14 of general relativity, although this is more like 2 lectures, honestly. There's a lot in here. So back to Carroll, and by Carroll, of course, I'm talking about this book here, right? Once upon a time, I had the domestic hardcover, and then sadly it was lost. It's a beautifully printed book, you know. It's a really nice book, but I don't know where I lost it to, and it is lost. So let's go on here. Anyway, so the way Carroll introduces covariant derivatives is, I think, pretty much the same way I saw covariant derivatives introduced in my relativity course at Stony Brook. And so there, the basic motivation was, hey, we're interested in partial derivatives in physical equations, and trouble is that if you study the coordinate change property of the derivative of this, that, or the other thing with respect to coordinate, well, you don't get a tensor. It doesn't transform as a tensor, and so that's a problem. How do you fix that? All right, and they say, well, we can add these coefficients, right, over here, and in so doing, if we construct these coefficients in a smart way, then we can make we can't make the partial derivative a tensor, but maybe we can make the covariant derivative a tensor. All right, and so that's the claim. And here's the claim. It's kind of it's a bit wonky, but it's kind of a standard idea. Given a vector, if you pick the coefficients over here in such a way that this transforms as a 1-1 tensor, all right, well then the transformation law for the coefficients is not tensorial. However, it's close. Well, this isn't really getting to the point yet. This is just kind of a confession. Okay, so the thing that you need to fix, I mean, it kind of makes sense, right? I'm saying that this doesn't transform as a tensor. So what do? Well, you find something else that also doesn't transform as a tensor, but in some sense they ameliorate each other's non-tensorial nature and give you something that altogether is a tensor. Anyway, so here we go. Supposing that this is a 1-1 tensor, that means that with respect to a general coordinate transformation, we have these transition matrices for the transformation law. So like here's the vector transformation law. V nu prime is partial x nu prime partial x nu contracted over v nu, since v is a type 1,0 tensor. Now in Minkowski space this is just a matrix, right? And so since that's just a constant matrix for like Lorentz transformations, when you differentiate it, you just differentiate right past the matrix and it's not an issue. But when this is also a function of space-time, when you take the derivative, then you get an extra term, and that's what spoils the tensor law. But anyway, so let's kind of dive into that. So here, if we're assuming that this is a 1-1 tensor, that means that with the primes, we can convert to unprimes if we contract against let's just call these transition functions, all right? And, but on the other hand, of course, this is by definition partial mu v nu plus plus gamma nu mu lambda contracted over the lambda v nu, v lambda there. And on the flip side of things, let's see here, I can, let's see here, boop, 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 boop. Let's see, where's this coming from? Okay, so this right here, right, by definition is partial mu prime contracted against v nu prime. And then you got your Christoffel term over here. Although we don't know that these at this point in Carroll, we don't yet know the formula for these. Gamma, nu prime, mu prime, lambda prime, like that. This is the derivative with respect to the prime coordinate, and remember that the vector in the prime system can be written in terms of the vector in the unprimed system contracted against the transition function like that. But then this guy gives you a product rule, so you got this second derivative term, and then the product of the transition function and the derivative in the primed sense of the unprimed coordinate v, and then we can convert prime derivatives to unprimed derivatives by the chain rule here. That's what that is. It's the chain rule going from here to there. This I just operated and just mentioned something. So what I'm doing here, I'm taking this right here, the derivative with respect to the prime coordinate, and I'm converting it to a differentiation operator with respect to the unprimed coordinates. This is the chain rule right here. That's what that is, right there, or right there, if you're interested in some Appalachian mathematics. Let's see here. I don't know if I should say Ewens or y'all. So we got the second derivative term over here, and the why? Sorry, I have lost track of something. I spent about 10 minutes. I wrote this about a day and a half ago, and it made sense to me when I wrote it down, but today I'm having trouble tracking back through what I did. I mean, I know that this is, I'm just unfurling this piece in terms of this derivative, which gives me that. And this piece is where is that gone to? Well, that's this. Fine. And then, so I was expanding this on this line separate, right? It can be this plus that, right? And then I think my point is that this and that will cancel. Like this term and that term will cancel. So I feel like it's giving me what's in blue plus what's in red equals to what's in purple over here. I mean, that, and yet I think the sign is wrong. Like, I'm supposed to get this up here. So I'm sorry, guys. There's something I'm just not seeing. Like I've spent, I don't know, spent a long time on this page. It's bothering me that I don't have it at the moment, but I got to go on. I'm so sorry, folks. But this can be derived. I checked it again. Like, I don't think there's a sign error in Carroll here. I wanted to put a minus there right now, but I don't think it's right. I think I'm just not seeing past something stupid on this page. So I assure you this, all of the kinds of calculations I'm making are the ones that are necessary to derive this. But I'm not able to see past some mistake I'm making here on this page right now. I'm sorry. So, all right. Recover from my stupidity. Let's go on here. So up next, observation that if the Christoffel symbol, let's just call it connection coefficients for the moment, transform as on 10, then if you define T nu mu lambda as this antisymmetrized difference, well, then that actually gives you a 1-2 tensor. So to check that, check its transformation law. What happens if you look at T in prime coordinates? Well, it's the difference of the gammas in the prime coordinates, which if we could just not be a dummy, I could get this again. I should have just said it with confidence, then you wouldn't have even questioned me, you know? But I know. Let's see here. So these guys cancel because you can commute the partial derivatives in the second derivatives, those commuting, and so you can make this sum and that sum match up because you can commute the partial derivatives and then swap the labels. It's just literally the same term, so they cancel. And on the flip side, again, swapping. Actually, I may not even be swapping indices here. I may be just using commutivity of the partials. I think I don't even need to relabel. Goodness, I've already got my made just to put that. Oh, anyway, this is not that interesting. Let me go on here. So basically factor this and that out, and then you get the difference of the gammas, which is the torsion here again. So the torsion tensor is something you can construct from connection coefficients if you got them, although the torsion tensor will be automatically 0 if you've got a symmetric connection. I should mention there is the current Wikipedia article on connections. It has all kinds of formulas there for like a connection that perhaps wasn't coordinate, things for non-coordinate frames and things. There's a lot of technology in the Wikipedia article that is not in Carroll. Just saying. I don't know if any of that matters at the moment, but just mentioning. Anyway, so the larger point here is the covariant derivative of tensors of type KL will form a new tensor of type K, comma L plus 1. And the rules for forming the covariant derivative are linearity, this Leibniz rule. It has to play nice with contractions. So whether you contract the tensor before and then take the covariant derivative, it should be the same as if you take the covariant derivative of the tensor and then contract it afterwards. It should reduce to partial differentiation on scalars. And I would add number 5 to this list. We'll use the Levi-Civita-Riemannian connection, so there's going to be a formula for calculating the connection coefficients in terms of the metric, or, well, its derivatives, I should say, and its inverse. So the rules above actually allow us to derive formulas for the covariant derivatives of tensors other than type 1,0 by our formula for type 1,0. And here, in some sense, I think Carroll exceeds Frankel in terms of its scope. Like the concept of covariant differentiation that Carroll sets forth is more general than the one that's in Frankel. At least the part I was looking at, because Frankel's pretty much focused on sort of the lowest order of these ideas, and being careful and formal about it, of course, but it's more of a math book. But here, we're going to see on this page, I derive, following basically the idea in Carroll, that if you have the covariant derivative of a vector, you can also derive the covariant derivative of a covector, because of this assumption that the covariant derivative on a scalar is just partial differentiation. So if we form the scalar phi, which is formed by contracting a one form with a vector like this, right? Well, that gives us a scalar, and so the covariant derivative is partial differentiation for that. But on the other hand, by the Leibniz rule, it's this plus that. But we already know the rule for this is partial derivative v lambda plus gamma lambda mu nu v nu. We don't know at the moment what the covariant derivative of the covector is, so let's just leave that arbitrary. And then from the product rule over here, I get this piece, which is the same as that piece. They cancel. Solve for the thing I don't know, and we can just divide. Basically, think of it. I know this is bad, but think about it. You can just kind of divide out the v lambdas. I don't. Let's not say that. Let's say because this holds for all possible vectors v, we can drop the v and just get the equation for the covariant derivative of the one form, namely this. So it's the same, almost the same formula, except instead of having a plus the Christoffel symbol term, we have minus the Christoffel symbol term. It's pretty snazzy. And I don't know, Carroll has some argument. He introduces a gamma tilde and shows the gamma tilde is minus gamma, whatever. I like this way. Carroll mentions, of course, that you can use this idea and bootstrap your way up to tensors of other type. Like type K, I'll tensor the covariant derivative in the sigma direction. Here's the formula. Basically, you just add Christoffel terms for each contravariant index, and you subtract Christoffel terms for each covariant index in this way. Well, I guess I should zoom in on that a bit because it's a little bit tiny. So notice the contraction over lambda. It starts out at the first spot, then it goes to the second spot, and it just keeps going to the kth spot in the plus dot dot dot. And down here, the contraction over lambda, first spot, second spot, and it keeps going L terms. So there's K terms up here, L terms down here, and then that one extra term over here. An application of that, right, would be the covariant derivative of the metric. And so there's the formula for that. Covariant derivative of a metric would be nabla sigma g mu nu is partial derivative with respect to sigma of g mu nu, and then minus 2 Christoffel terms, right? Contract the lambda over the first index, contract the lambda over the second index, like so. And so, incidentally, now that we've worked our way up to that, you can see that demanding that the covariant derivative be covariantly constant, right? Demanding that the covariant derivative of the metric is 0 for arbitrary indices, it equates into the partial derivative of the metric being equal to this particular, sum of contractions of the metric against the Christoffel symbol. This is exactly the formula that we derived from the theorem from Frankel, where he assumed that, the derivative. Let me just get back to it, because that was like 30 minutes ago, wasn't it? Where's that thing? This guy right here, back on page. This condition right here. Now, what this condition says. So, I guess we're still not ready for what this condition really means. This becomes really interesting in terms of parallel transport. See, because if x and y are parallel transported, that means that like nabla x dt is 0 and nabla y dt is 0. So that makes this 0 and that 0, which then makes the time rate of change of the inner product between x and y 0. So like, if the connection has this property, then you have two parallel transported vector fields. Well, then the inner product between those vector fields is held constant along the parallel transport, which is interesting. Anyway, so here we go. So we've got the covariant derivative of a metric, looks like this, which then if it's 0 gives us that, which is neat. Again, you compare to page 8, this is the formula that we use to derive the Christoffel symbols, actually. And so again here, if you want to insist that your connection is such that the covariant derivative of the metric is 0, well, you set this equal to 0, which gives you these formulas, and then you add it together with itself with this pattern, and then subtract once, you get cancellation of things, and assuming that it's a symmetric connection, then you wind back to this formula again, which is our standard formula for the Christoffel symbols in terms of derivatives of the metric. Notice the pattern is nice here. So mu nu, check it out. So we contract over rho, so we do mu nu rho, and then it's like a cyclic permutation, right? So I push the nu over here, nu, rho, mu goes to the end, right? And then I just push it again. See, rho, mu, nu, the pattern, there's a nice pattern here to see that it's easy to remember. And then it's just plus, plus, minus for... I'm sure there's some master teacher of relativity out there who has this wonderful explanation for why it's plus, plus, minus, but I'm not that guy. All right, so example. What, an example? How'd they get in here? Can't do examples. All right, so the plane with polar coordinates. So dr squared plus r squared d theta squared is the metric in polar coordinates. So here's your coefficients. I'll just write them out as a matrix for convenience of exposition. Here's the coefficients of the inverse matrix. Since diagonal matrices are really easy to invert, you just flip the diagonals. I think all of the examples in this lecture are of this type, which is kind of lame, but that's what I have for today. Sorry, but the Christoffel symbols, then we use the formula, and it's just zero. Everything's zero because either the derivatives are zero because GRR is 1. So if it's 1, you differentiate it at 0, right? So this is just obviously 0. Derivatives of 1 are 0. And then over here, like r theta or theta r, those are just literally 0 because they're the off-diagonal elements of this guy. Now GRR is r squared. That's lovely. That's actually variable. But then you're taking the theta derivative of it. So it's just 0. Now in contrast, the r theta theta component of the Christoffel symbol here is this. And let's see here. So the interesting part, again, because r theta is 0, the only thing this contraction over rho reduces just to rr. So gur. And then let's see here. So that just the only non-trivial term here is grr minus partial r g theta theta, which is r squared. So that gives you a 2r. And then the 2 and the half cancel and leave you minus r. And similarly, the calculation of the other Christoffel symbol, theta r theta, like this, gives us 1 over r. So that's kind of that. Here's an interesting homework problem that should be relatively simple to do. Calculate the try to calculate the Ricci scalar for this example. All right, that's a good problem to try. Now I haven't defined the Ricci scalar yet, but we will shortly. So once you do, come back to this example, unnumbered page 13 example. Try to calculate the Riemann tensor, the Ricci tensor, and the Ricci scalar. It should be relatively simple to do that, although I think it may not be that interesting to do. I don't think it's going to be interesting anyway. Okay, so you're like, you want me to do something uninteresting? Well, it might be instructive, I don't know. Let's see here. So the covariant divergence of a vector is nabla mu v mu. And I don't know what this much has to do with anything else in this lecture, but I worked it out, and I'm going to talk about it here because it took me an hour. So, so anyway, here's a theorem that the covariant divergence is 1 over the square root of the determinant of the metric times the partial derivative of the square root of the determinant of the metric times v mu. And so the covariant derivative is this. And then Carroll says it's straightforward to show that if you contract the Christoffel symbol over mu like so, it's equal to 1 over the square root of the determinant, the absolute value, the square root of the determinant times the partial derivative of the square root of the determinant. And I said, oh, okay, straightforward. I know what these things mean. I can calculate it. I've even got snazzy index formulas for the determinant, right? Yeah. I believe this is what we call a joke. So let me show you why this is true. But we'll come back to this. Let's just finish the thought. Suppose that star is true for a second. Well, if star is true, then if you have this plus that, well, then it's fairly obvious that it's really just the partial derivative of this times that, because you can work backwards. This is just the product rule. So like you've got, see, the one of the product rules in this would just be like square root of the determinant times the derivative of v mu, but the square root of the determinant cancels the square root of the determinant, just leaves you that. And then the other term in the product rule is exactly this. Sorry for my ugly muse. Now, this is interesting because it's used in the curve space Stokes theorem, among other things, which says that the integral of the covariant divergence over some set of space-time, it's equal to the integral over the boundary of the space-time. And this is the normal, and so forth. I'm not sure this is space-time or it's actually just a spatial result, actually. But anyway, here's why it's a joke. So to derive that formula that I just had on the last page, star, here's what I had to do. I had to remind myself that if we're differentiating a determinant, it's in fact the determinant times the trace of the inverse matrix times dA dt. This is an identity that you can prove for the derivative of the determinant of a matrix. And as such, when you take the partial derivative of the determinant of G, it gives you the determinant of G times the trace of G inverse times the partial derivative of G. But this is really just the trace of this matrix, like so, and the formula for the trace of this matrix, like so, is exactly given down here, Gij, partial lambda Gji, like so. And so if I do 1 over the determinant, square root of the determinant, then I do derivative of the square root of the determinant by the chain rule. It's 1 over twice the square root of the determinant. And then I do what? I do times the determinant times, so now I'm using this right here, right? Just a second. So I've got this right here is equal to this right here, which means I can take this right here. Oh, no. Blast. This right here is what I meant to underline. Now I've got to undo that under other underlining because it is not helpful. All right. Get out of here. Yeah. Be gone. There. So they get this. There's some cool cancellations that happen here. Like you get square root times square root gives you the thing, then the thing over the thing gives you 1, and then you've got this half, which survives like so. And then when you look at the contraction of the Christoffel symbols over here, like such, then, well, 2 of these dudes just cancel, and then that leaves you the one in the middle times a half, which is this, but that, my friends, is straight up what we have right here, which means it is literally 1 over the square root of the determinant times the partial derivative of the square root of the determinant. So yeah, really straightforward. Really straightforward there. So, I mean, maybe it's straightforward if you've had like a awesome class on like calculus of matrices and such, right? We've all had that class. I don't know. I almost feel like when a physicist says in a book it's straightforward, it almost means the opposite. think it tends to mean here's something that is technical, tedious, and I just don't feel like showing. I don't know. But anyway, I know Carroll is working from somewhat. His book is somewhat based on Wald's relativity book, and I was looking at Wald. And Wald actually does have some details on that. But anyway, moving on here. So let's talk about parallel transport and geodesics. Now, I will give another lecture on the properties of geodesics and such, separate from this lecture. So I'm just going to talk about it here, but we'll revisit it again more fully. All right. But here it is. So you can define this, derivative along a curve like this in just Euclidean space, but to make this tensorial in a curved space, we have to replace the partial derivative with covariant derivative, right? Because we know this will give us a tensorial equation, and that's what you like, because you want to write equations which are true in any choice of coordinates that you make. So here it is. This defines the derivative of the tensor over a curve with parameter lambda in terms of the contraction of the covariant derivative with the velocity vector to the curve. And if that's 0, then you say that the tensor is parallel transported along the curve with parameter lambda. In the case of a vector, it just looks like this. And if such a vector field is given along such a curve, well, then that vector field is said to be parallel transported along the curve. All right, so, and what is a geodesic? Well, a geodesic is a vector which parallel transports its own tangent vector field. That is to say that this equation, the geodesic equation, holds true for its acceleration relative to its velocities contracted against the Christoffel symbols. That's a geodesic. And so those are important in relativity because those play the role of lines, and they have a special place at the table, so to speak, in the discussion of physics. And we'll talk more about that in a future lecture. I'm just going to leave it there for the moment. Geodesics are important. We'll come back to them. But there's a connection here between the curvature tensor and the parallel transport idea. In particular, Carroll introduces curvature in terms of this. He says if you transport a vector around a loop, we've seen that, like on a sphere, if you look at the transport of the vector around the quarter sphere, you get back to something you didn't start with. And the reason for that is because the sphere is curved, right? So how do you capture that idea in general? Well, maybe you should look at an infinitesimal loop and study how vector is transported. If you take a vector v and you transport it along this little path, this little path, this little path, and that little path, what does that get you to? Well, it seems like that should be proportional to the size of A, the size of B, and of course the size of the vector that you're transporting. And that straight away leads, and the answer should again be a vector, so that leads you to a vector valued function of 3 inputs, which gives you this type of tensor, right? But then since we want to do this in a tensorial fashion, then the natural thing to try is the version of this, but with covariant derivatives. Think about how does it change in the, if we study the covariant derivative in the mu direction, followed by the nu direction, followed by the minus mu direction, followed by the minus nu direction. Well, that's what this is. And so then you can work it out, as I do here, in all of its glory. Get out of my way, paper. Yeah. So I take these nested covariant derivatives and you work it all out. Some things are going to get like lumped into over here, So like here I've got, so I'm only writing the mu nu, and then the next term is flipping the mu and the nu. So like these two terms are you've got your gamma, lambda, mu, nu, and then you've got this piece and that piece. That's exactly the covariant derivative in the lambda direction of v rho. See that? So those two go into, and then you got the opposite with the nu and the mu flipped in this other term here. So that goes together to give you the red term. Like the green term is, it again has its antisymmetric partner over here, and that gives you this. Let's see here. Well, it gives you this and that, right? This is the green term. Here's its nu flipped with mu partner. Here's this term, and it's flipped nu and mu partner here. And then I believe the other terms, like this one, this one, this one, they all cancel with corresponding terms in the mu and nu flipped. All right, and so long story short of this, what we have is that when you calculate the commutator of covariant derivatives, mu and nu respective directions, acting on vector v nu, v upper row rather, what you get is this, type, this tensor, r rho sigma mu nu, contracted across v sigma, right, where the r rho sigma mu nu is defined right here in terms of derivatives of the Christoffel symbols as well as products of the Christoffel symbols. And then there's also this other piece over here. And I really shouldn't say Christoffel symbols, I should say connection coefficients, because as Carroll points out, the derivation doesn't assume that they're Christoffel symbols really. Fair enough. And so there's also this torsion piece over here from the because that is the torsion tensor, right? So there it is. And then Carroll actually says, well, and in fact, this is just the first step. And you can look at how this operator, the commutator of nabla mu and nabla nu acts on tensors of higher type on page 123 is equation 3.114 has the higher order version of that there. So let's talk about it. What we got next here? Simply connected semi-Riemannian manifold. There exists a coordinate system such that g mu nu is constant if and only if the Riemann tensor is 0. All right. So I wanted to kind of sketch out the argument that's given in Carroll here because I think it's interesting. And although I will say that this argument will make a little bit more sense after you've processed the lecture that I will make on parallel transport. So I'm jumping around a little bit in Carroll. I'm trying to just gather together everything about the curvature here in this lecture, more or less is what I'm after. Whereas he has things sort of scaffolded through the chapter where he kind of goes back and forth between the parallel transport and then does a little bit of curvature and then does more parallel transport, does the example of the, interesting physical example there. And so I'm reordering things a little bit better to try to make it more confusing. So I hope it worked. Anyway, so here we go. Forward implication. Well, if this forward implication is really easy. If your metric is constant, then the Christoffel symbols are straight up 0, which then means when you take derivatives and products of Christoffel symbols, you get 0 again. So the curvature tensor, in fact, the Riemann tensor is 0. The other way around is interesting. If the curvature tensor is 0 on some simply connected region of a semi-Riemannian manifold, then point number 1 is if we construct a one-form field by parallel transport. So this is what I'm talking about here, this construct the one-form field by parallel transport. That idea we'll dive into a little bit more in a future lecture, so my bad, all right? Then that's possible over the whole manifold essentially by the path independence of the parallel transport. The reason that the parallel transport is path independent here is because the curvature is 0. So you can kind of get the idea in a fuzzy way from the loop thing we were just talking about. Just trust me on it for the moment. Like I said, it's kind of a sketch. So okay, so if you can take this one form field, parallel transport it, right? then you can parallel transport it, and you can basically parallel transport it, right? So that means that the covariant derivative of the so constructed one form field is 0, which then means this is 0, which then means the exterior derivative of this parallel transported one form is 0. But hey, if the exterior derivative is 0, that means it's a closed form. And since we're on a simply connected region, closed implies exact, which means that there exists a phi such that omega is d phi. All right, so that's like ingredient number 1. You can essentially create these global exact forms. Any one form can be, made into a, not any one form, but a one form constructed from parallel transport can be made into a exact form, all right? And then point number 2, as we talked about before, Sylvester's law of inertia says you can find a frame at a point such that you take the metric and put it into, just ones and minus ones down the diagonal, right? And since we're assuming our metric is non-degenerate, there's no zeros on the diagonal, it's just 1 or minus 1. And then the thing is, you basically just take this thing and parallel transport it everywhere. And that gives you, the thing is, we're assuming it was the metric at the point to start with, right? And since we're talking about a metric connection, it's still the metric after you parallel transport it, essentially. But anyway, so the parallel transport still gives you the same formula, all over m, and then Carroll's like, well, that's not a big deal. I mean, you can do that on any manifold, but the thing is, you can't do that on any manifold, and also, in addition, have that the thetas are likewise differentials of coordinates, and that's what we do get here because, again, we're using parallel transport to construct the theta. And as such, theta is exact, which means that the derivative of the functions, which are its potentials, those are the coordinates that you're looking for, such that the metric's constant. Now, so I thought that was a kind of neat argument. And then page 19 here. Here I collect all of the properties of the Riemann tensor. So I think Carroll spends about 3 pages really diving into some of these. I'm just going to kind of give you a quick overview. So here's our formula for the Riemann tensor, right? There's the basic formula. And sometimes it's interesting, well, it's always interesting to notice that it's antisymmetric in its last 2 indices. That's like manifestly true from the definition. You can also lower an index like this to give you this completely the covariant Riemann tensor, if you want to call it that. And so then Carroll mentions the following, that the covariant Riemann tensor is also antisymmetric in the first 2 indices. So, and it's still and by the way, of course, this guy is also antisymmetric in the last 2 indices as well. I guess I should probably write that a second here. It just seemed too obvious to write when I wrote this earlier, but it's also true that if we have rho sigma mu nu is equal to minus r rho sigma nu mu. All right. And then the other interesting symmetry of the covariant version of the Riemann tensor is that you can flip both pairs. Like, you can take mu nu and shove it over here, and take rho sigma and shove it over there, and that's also equal. You also have this guy right here, which is, if you notice, rho is fixed, and we're cyclically permuting the sigma mu nu sigma mu. This is the Bianchi identity, which you could rewrite as the complete anti-symmetrization of the last 3 indices like such. This takes Carroll a little while, but he argues that there are 1 over 12 n squared times n squared minus 1 independent components of the Riemann tensor. So in dimension 4, that gives you 20 degrees of freedom. That's not an accident. That just nicely matches the degrees of freedom for the second derivative of the metric that we saw back in chapter 2. Remember, um, we could choose coordinates, I think, if I remember right, to make the first derivatives of the metric to be 0, but we couldn't force the second derivatives to all be 0 at a point. And it seems like that is the obstruction of doing that is exactly the degrees of freedom which are captured by this curvature tensor. I guess it's also interesting, I meant to work this out, what happens when you put n equals 2 into this? What are the degrees of freedom for the Riemann tensor in dimension 2? That's 4. 4 minus 1 is 3. 3 times 4 is 12. 12 over 12 is 1. So in dimension 2, the Riemann tensor is really only as interesting as the scalar which underlies it, right? Which is what I defined down here, the Ricci scalar. So the Ricci tensor, you contract this pair of indices in the Riemann tensor, that gets you the Ricci tensor. Then you contract, let's see here, well, where's my Ricci tensor? What even is that? Oh, that's this. Okay, so this is defining that. Fine. Anyway, so that's the Ricci scalar. Apparently, in dimension 2, the Ricci scalar has as much information as the Riemann tensor. And then there's also this Einstein tensor, which we'll talk more about when we talk about Einstein's field equations. We need this Einstein tensor to do that. Interestingly, the covariant derivative of the Ricci tensor is 1/2 the covariant derivative of the Ricci scalar. It's kind of a neat relation between the Ricci scalar and the Ricci tensor, and that is tantamount to why the covariant derivative of the Einstein tensor is 0. You can almost see that if you just kind of look at this, look at that. So like if you contract, take the covariant divergence of this equation, I think the first term is that, and then you get like minus 1/2. And remember that the g is constant, so essentially it factors out of the covariant derivative. And, well, there's like, you notice they're also playing this game with raising and lowering the indices on the nabla. So, a lot of things going on in that formula. But I think we'll come back to that one. All right, as if this lecture is not long enough already, some examples. So here's my token four-dimensional example for you, which is very silly. So R3 R3 cross product with the Cartesian product, rather, with the circle of radius r. A nice metric for that is just this: dx squared plus dy squared plus dz squared plus r squared d theta squared. So I'm using theta as a coordinate on the circle. Then the components, well, they're all constant, right? And so yeah, that means that the derivative of the metric are all 0, the Christoffel symbols are all 0, the Riemann curvature is all 0, the Ricci curvature is 0, the Ricci scalars, it's all 0. I think that's how the example on page 13 will work out once you get past, like the Christoffel symbols were non-trivial for the example on page 13, right? But I think when you get to the calculation of the Riemann curvature, it's going to be 0. So that's my intuition there anyway, because it's just a funny metric for a flat space, so it shouldn't really be genuinely curved. I mean, it's possible to have non-trivial connection coefficients, Christoffel symbols, on a flat space. But if your space is genuinely flat, the Riemann tensor will be 0. That was the theorem that we just sketched a couple pages ago, right? So let's see here. Example 2 is a sphere with, well, what's his name? Carroll calls this the round metric. And so, like, here's the components for the metric a squared and a squared sine squared theta. And so if I take the derivative, I get this and that. The inverse metric, you just flip the diagonals, so you get that, right? So really there's only one interesting derivative to look for, which is partial theta g phi phi. And so when I calculate the connection coefficients here like such, there's only this term to really look at. These are obviously, these are like just automatically 0. And so we're just left with sine theta cosine theta with a minus up front. And this other one, again, it's diagonal, so unless you got theta theta or phi phi, these are automatically 0. And g phi phi is that. We're taking the theta derivative, so again, it's that same derivative. And we end up with a cotangent theta there, which is interesting, because when you calculate the Riemann curvature for that guy, like so, according to the formula, you know, let's see here. I'm only keeping track, I think, of the, let's see here what I do. I guess there's no, that's right, there's no, goodness gracious. Let's go back to here's the formula, right? So you notice the first two terms there's no sum, right? It's just these indices again in that pattern. Then there's a sum over lambda for these two, all right? So the last two, we've got to think about a sum. These two, we just have to reproduce that pattern with respect to these indices. So that's what I've done here. All right, not done here. To reproduce the pattern, and then here I've got a sum over lambda, but the thing is, I only have the only non-zero Christoffel symbols are the ones I've written here and here. And of course this is also, well, you know, there's three. This, and this. And, all right. So I get partial theta of that, because that's what that is equal to. Theta phi, that is, well, it's cotangent theta. When I differentiate it with respect to phi, that's 0, right? So that's gone. And let's see here, so that lambda, it's a theta and a phi, but notice that these are both 0, so that's irrelevant. Wait a minute, no, that one's, well, this one's 0, but that one is non-zero, who cares? That one's 0, this one's non-zero, who cares? I mean, as long as one of them's 0, it's out, right? And then, let's see here, so theta, phi theta, don't think that's I think that one's 0. So this is 0. This one must be the one. Theta, phi phi, phi theta phi. Yeah, that's the one. So this one counts. It gives you this times that. But notice that the cotangent, this is cosine over sine. So this gives you a cosine squared. So you get plus cosine squared minus cosine squared. They cancel. They just leave you the sine squared. So there you go. There's the Riemann tensor. So it's, you know, I've added a little bit of calculation that Carroll didn't show, but nothing terribly profound. You know, he didn't say that this was straightforward. So it must be easy. It's yours. So here's the covariant version. It just gives you that. And he says you can check other components are either 0 or can be obtained from the above. Here's how. Like anytime you have a repeated index in an antisymmetric pair at 0, and that's true like this pattern with whatever lambda and alpha you got there, and it's still going to be true when you lower the lambda, and you know, either starting or end, and basically anytime you've got a repeated index here, it's going to be 0. And so all that really leaves us is these patterns like phi theta theta phi, phi theta theta, theta phi, or theta phi theta. All of these are a squared sine squared phi. And so with all of that in mind, we can go ahead and calculate the Ricci scalar, a Ricci tensor rather. We do so here. Our theta theta is g phi phi. And I explain better in the next one, but it works out to this for essentially the reason down here. And that gives you 1. Let's talk about this one more. So r theta phi. is by definition I contract over the lambda and leave the theta and the phi put, right? But that is also equal to g beta lambda r beta theta lambda phi. But remember, the only way that this can be non-zero is if the beta and the lambda are respectively phi and theta from what we have up here. So there you go. And then that is, but the thing is, okay, well that's lovely, but that doesn't help us because g phi theta is 0. So great, those are 0. Now r phi phi, by the same kind of logic, we've got beta lambda contracted over r beta phi lambda phi. So in order to make this come out to non-zero, I need both this and that to be theta, which is interesting because then that makes that g theta theta, which is 1 over a squared because of what was on page 20. See, g upper g theta theta would have been this guy, 1 over a squared. 1 over a squared, and then that was a squared sine squared, so we get sine squared theta. And then finally the Ricci scalar contracting like so, we end up with 2 over a squared. So long story short, the sphere has a constant scalar curvature of 2 over a squared. The final page. So last but not least, we talk about the Poincare half-plane with metric, which is actually variable for change. A squared over y squared, dx squared plus dy squared. I guess the last one had variable metric too. Let me not short sell it. So here's my matrix for the metric, for the inverse metric. And you can calculate the Christoffel symbols like such. They work out to minus 1 over y, 1 over y, and minus 1 over y. And then you can calculate, much as we did in example 2, I won't show the details this time, that the Riemann tensor is actually minus 1 over y squared for this xy, and the Ricci tensor has xx equal to minus 1 over y squared, the xy component 0, the yy component's minus 1 over y squared as well. And so that gives you a Ricci scalar, which is minus 2 over a squared. And that's interesting because it's constant. Just like the sphere had constant curvature, this has constant negative curvature. And this is actually, a well-known example in differential geometry. It's an example of a hyperbolic geometry. It has geodesics, which are vertical lines, but also these half circles, actually. He says it's clear that the geodesic equation has that as a solution. Definitely, if you'd like to do that as a homework problem, go for it. Show me that this is a solution to that. I'd love to see it. Details not in Carroll. Now, he does essentially have this calculation, which is the arc length of a vertical line segment with respect to the Poincare metric here is the natural log of the quotient of the y's. And that I think we derived in the previous course. But anyway, just to summarize things here, I think it's interesting. We have seen for Euclidean signature, we've actually seen the examples of maximally symmetric spaces in this lecture. At least we saw the sphere and we saw the hyperboloid. That's this example is the hyperboloid. Actually, it's a model for the hyperboloid. And so that's a space of constant positive curvature, a space of constant negative curvature. If we were to study the plane, it would have constant curvature 0, right? Euclidean signature, because it wasn't. That means that the metric actually is a Riemannian metric, okay? In contrast, if we had Lorentzian signature, which means that like Minkowski space, for example, it has that Minkowski metric with the Lorentz signature. There are also spaces of constant curvature called de Sitter space and anti-de Sitter space with positive and negative constant curvature. And then in the middle of those two, the analog of flat space for Lorentzian signature is Minkowski space. That has constant curvature 0 in this sense. Well, that's it for this time. So thanks, guys.